Alright, so let's look at example 3. The edges of a cube are expanding at a rate of 5 centimeters per second. We want to know how fast is the surface area of the cube changing when each edge is 3 centimeters and 7 centimeters. So the first thing we need to do, as always, is draw out a picture. So in this case, we know we're looking at a cube. So draw out a cube. And we know our sides are all going to be the same, so I'm just going to call them X. Because it's a cube, they're going to be the same. Alright, so that's our picture. Alright, so the next step we need to figure out is what do we know? So in this case, we know edges of the cube are expanding at a rate of 5 centimeters per second. So our edges, we said, were x, so this is going to be dx dt. So we know dx dt is positive 5 centimeters per second. Since it told us it's expanding, that means it's going up, so it's going to be positive. Alright, what do we want now? So we want the how fast the surface area of the cube is changing. So I'm going to use dA dt for that, where A is representing surface area. So we want dA dt when the edge is 3 centimeters, so x equals 3 centimeters, and whenever x is 7 centimeters. Alright, so to find this now, so we need a formula for surface area. So remember, surface area is nothing but the sum of all the areas on the shape, or on the figure. So in this case, if it's a cube, it's going to be the sum of the areas of each of these 6 squares. So in this case, surface area is going to equal to 6 sides because every area is the same. So just 6, and then the area of the side is x squared. So our surface area formula for a cube is just a equals 6x squared. All right. Step 5, implicitly differentiate both sides of this equation. So the derivative of area with respect to time is dA dt equals 12x dx dt. At this point, I'm assuming you should know how to implicitly differentiate and to how to take derivatives, since that was on test 2. So you should know how to do that. So I expect you to know how to do that. That's why I'm not working through all the steps of how we implicitly differentiate this. All right, so we've got our related rates equation now. So the last step is sub in. So for part A, whenever x equals 3 centimeters, then dA dt is equal to 12 times 3 times dx dt, which we said was 5. And this is going to end up being centimeters squared per second. So the 3 centimeters, 5 centimeters squared, 5 centimeters per second. So we end up dA dt is 180 centimeters squared per second. All right, part B, whenever x is 7 centimeters, exact same process, just substituting in what we know. So dA dt is 12 times 7 centimeters now, times 5 centimeters per second. So dA dt then, whenever x is 7 centimeters, at that instant, the surface area is changing at 420 centimeters squared per second. All right, example 4. So given a cone whose height is 3 times its radius, and whose radius is increasing at a rate of 3 inches per minute, we want to find the rate of change of the volume of the cone when the radius is 6 inches. So step 1, draw our picture. So just think of an ice cream cone flipped upside down. So here's our radius of the base, and then the height of the cone. And so what do we know now? So we're given a cone. The height is 3 times its radius. So we know h is 3r. And the radius is increasing at a rate of 3 inches per minute. So the radius is increasing. So dr dt is positive 3 inches per minute. And so what do we want now? Step 3. In this case, we want the rate of change of the volume, so we want dV dt when the radius is 6, so when r equals 6 inches. All right, so step 4, figure out what equation we're going to use. In this case, we're dealing with volume of a cone. So volume is equal to 1/3. Started out with the volume of a sphere there. So 1/3 pi r squared h. Now, if we think about this, so if we were to go ahead and just jump straight to step 5, start implicitly differentiating this, what's going to happen? We have 3 different variables here, right? So we have volume, we have radius, and we have height. So if we were to implicitly differentiate this, we would end up with something that's going to involve dV dt, dr dt, and dH dt. So you might be wondering, okay, what's the problem with that? Well, let's look at the information that we have. We know stuff about the height. We know dr dt, right? So we know height is 3 times the radius, but we only know information about rates for dr dt, and we know we're going to want dV dt. So if we were to try to solve this by just going straight in implicit differentiation, what's going to happen? Well, we'd end up with that dH dt in there, and we don't know anything about height's rate of change, do we? So because we don't know anything about height's rate of change, we would have 2 unknowns in one equation, which means we couldn't solve the problem, right? So what do we have to do? To fix that, we have to eliminate one of the variables somehow. Well, to figure out which one to eliminate, let's look at what we know. We know dr dt, right? And we want dV dt. So which of those 3 rates of change does not belong? That's right, dH dt. So we need to eliminate height from our volume equation. So to do that, well, can we rewrite height in terms of another variable? That's right. So we know height is 3 times the radius, right? So what that's going to do is that's going to let us then rewrite our equation. So volume then, substituting in what we know, is pi r squared times 3 times the radius, right? Because height was 3r. So cleaning that up, we get volume is equal to pi r cubed. All right, now that we have our volume equation in terms of only the 2 variables, volume and radius, now we can go ahead and implicitly differentiate both sides of this equation. So step 5, so the derivative of volume with respect to time implicitly is dV dt equals 3 pi r squared dr dt. And now we're good. We can substitute in everything we know. So the last step, so we want dV dt. We don't know that. So dV dt is equal to 3 pi times the radius. We want it when r is 6 inches. So times 6 times our dr dt. So times 3. And this is going to end up being inches cubed per minute. So dV dt, we end up with multiplying all of this out. And sorry, that's 6 squared since it's pi r squared. So we end up with 3 pi times 36 times 3 inches cubed per minute. So dV dt then, whenever at the instant that the radius is 6 inches, our volume is changing with respect to time 324 inches cubed per minute. All right, example 5. So a fish is reeled in at a rate of 1 foot per second from a point 15 feet above the water. At what rate is the angle between the line and the water changing when there is 25 feet of line out? So if we look at this one, well, we've already got our picture drawn for us. So that's step 1. And so notice in this case, our line going out from the end of the fishing rod is X. The end of the fishing rod, so the tip of the line, is 15 feet above the water. And theta is our angle between the water and the line. And even though they didn't draw it on here in the picture, the bottom of our right triangle is the water line. So step 2, let's figure out what we know. So we know a fish is reeled in at a rate of 1 foot per second. So in this case, the fish being reeled in, so think about what's happening. Which of those sides is changing? So X is changing, right? So our fishing line is coming in as you're reeling the fish in. So dx dt. And in this case, it's reeling it in. So that what's happening to that line? It's getting shorter, right? So that means dx dt is going to equal to negative 1 foot per second. And what do we want? We want the rate of the angle between the line and the water changing. So d theta dt when there's 25 feet of line out. So when x equals 25 feet. All right. So now let's go from there. So we need an equation that relates the side with our line and our angle. So let's use the two sides we know. So we know, in this case, based on where theta is, we have our opposite side and our hypotenuse. So that makes the most sense in this case to use sine theta. So sine theta, we know in this case, is 15 over x. So we can go ahead and substitute that 15 in, because what do we know? That fishing pole's not getting any closer or any further away from the water, right? That side is constant, so we can go ahead and substitute in 15 there. So 15 over x equals sine theta is our equation. So now let's differentiate. So the derivative of sine theta with respect to time is going to be cosine theta d theta dt equals, and if you think about 15 over x, it's 15x to the negative first power. Differentiate that, right? You're going to get 15 over, negative 15 over x squared dx dt. So step 6, we need to start substituting stuff in. So you might be thinking, well, we don't know what cosine theta is, right? So we don't know what theta is, so we certainly don't know what cosine theta is, or do we? Well, think about our relationships, right? So cosine theta in respect to the sides, so keep in mind, at this point in time, so whenever x equals 25, we now know 2 of our 3 sides of our right triangle. So how can we figure out? So if we think about what cosine theta is, if I call this the waterline y, cosine theta is what? It's going to be y over 25. So how can we figure out what y is? Right? So when x is 15, we know by the Pythagorean theorem, y squared equals 25 squared minus 15 squared, right? So y squared is 625 minus 225. So y squared is 400. So that means y ends up being 20 feet. So y is 20 feet whenever x is 25 feet. So then what's that mean about cosine theta? So cosine theta then, well, we just said it's y over x in this case. So it's our adjacent over our hypotenuse. So our adjacent side, we just said, is 20 feet. So it's 20 feet over 25 feet. So, and then simplifying that to make our life easier, cosine theta then is 4 over 5. So now we can sub in for cosine theta. Even though we don't know what theta is, we can find cosine theta. So cosine theta is 4/5. We don't know d theta dt. That's what we're trying to find. And that's equal to negative 15 over 25 squared times dx dt, which we know is negative 1. So 4/5 d theta dt equals, so go ahead and multiplying and simplifying, equals 3 1/25 on the right hand side. And so then dividing by 4/5, which is the same as multiplying by 5/4, right? So d theta dt equals 3 1/25 times 5/4. So d theta dt, cleaning that up, equals to 3/100ths. And in this case, our units are going to be radians per second. So you couldn't easily get that by plugging in your units. But in this case, you just know theta. We're always going to measure theta in radians in this class. So it's going to be 3/100ths radians per second, or as a decimal, d theta dt. In this case, because it's pretty easy to do, is 0.03 radians per second. And we're finished.